Hi there, welcome to lecture 22 of Fox, where we're going to begin the next journey in this course, the next part of this course. So for the last 20 or so lectures, we have been covering intensely discrete math. And where are we going next? Okay, perhaps the most important application of discrete math in the 20th and 21st centuries, the digital computer. So we are going to build and analyze a model of the digital computer. We're going to study what are the capabilities of computing. Okay. And we're going to begin this study in what might look like an unusual way. We're going to start by talking about infinity. Infinity? What does that have to do with computing? A computer is this finite object that's sitting in front of us doing all kinds of fancy things. Why do we need to study infinity? Okay. And so, let me address that a little bit, but it'll become clear through the course of this lecture how infinity is going to come back and have a lot to say about the capabilities of computing. Okay. Now, if someone were to ask, well, what is computing? Okay, so, the first thing that might come to mind is, it's the study of the digital computer. But it was Dijkstra who said, to say that computing is about the study of digital computers is like saying that astronomy is about the study of telescopes. No way. Computing is not about the study of the digital computer. The digital computer is just how today we choose to implement some of the things that we would like to do and things that we call computing. Okay. But computing is the study of algorithms. But what's an algorithm? Well, we don't have a definition yet, but Stephen Klein, gave a very beautiful definition of what is an algorithm in just one sentence. He said, an algorithm is a finite answer to infinitely many questions. How beautiful is that? Okay, so let's think about that a little. Think about a sorting algorithm. A sorting algorithm. So you have a sorting algorithm. You implement it as a program on a computer, but what does it do? It takes as input a list and produces a sorted version of the list. So there's an input and then there's the output. And you can think of the output as the answer. Okay? And this algorithm has to produce the correct answer for infinitely many inputs, because there are infinitely many different input lists that we could create. So an algorithm is a finite answer to infinitely many questions. And there you already see a hint of how infinity plays a role. How can we sort of build finite answers to infinitely many questions? So infinity is going to come in and have some role to play. Okay, so we're going to begin this journey, the study of computing, the theory of computing. And essentially we're going to follow the path that was laid for us by a famous guy by the name of Alan Turing. This guy is that famous. Okay, we have named the pinnacle of this sport after him, the Turing Award. If you can win the Turing Award, you're done. You don't need this book. You don't need this course. You're set for life. Okay? So go try to win the Turing Award. That's the pinnacle of the sport. But that tells you something about what this guy has contributed to the field. Okay? He basically gave us the theory of computing. He gave us a lot more. Okay? He helped England win the war against the Germans with his code-breaking abilities. He gave us the Turing test, which defines the intelligence in AI. Okay, so it's a test for intelligence. Okay, so he gave us so much. He gave society, he gave humanity so much. It turns out that his life was a tragedy, and you can read more about it in the text. You can read about it on the internet. He was burglarized. The police, in investigating the burglary, found out that he was gay, and strangely, at that time, that was not allowed. Okay. People were so closed-minded, they were not tolerant of other people's ways of life, other people's views. And so instead of, prosecuting and arresting the burglar, they prosecuted and arrested Turing. And he's the one who was punished. Okay? And, he went into depression and so on and so forth. Ultimately, he committed suicide. What a tragedy to lose such a brilliant mind at such a young age. Okay? It just shows that there's a lot to be gained by being tolerant. But anyway, you can read more about that on the internet, in the text. We are going to begin our study of Turing's theory, our study of the digital computer, our study of what is computing. Okay, now, before we get going, let me just give you a quick summary of the last 20 or so lectures. Okay, we studied discrete math, and it was really a short stroll through discrete math. Okay, we talked about precise statements and proof. Okay, and then we introduced this all-powerful proof technique, induction, very powerful for proving for all. And then we talked about, and induction plays a role everywhere in discrete math. We talked about, recursively defined structures. We talked about sums and asymptotics and the relevance to computer science, number theory and cryptography, graphs as, a fundamental way to represent relationships. All kinds of problems we like to solve can be represented as graphs. We talked about counting and how important counting is to, basic analysis of algorithms, and how important, what a beautiful subject counting is in general. And in fact, counting is going to play a role in today's lecture. Okay. Okay, and then we talked about probability. It's a relatively new injection into computer science, but I'll just give you some quick pointers to why we study probability. So real-world algorithms involve randomness and uncertainty. The world is, random. The world outcomes in the world are sort of uncertain. Inputs arrive in a random order. And nowadays, we have what are called randomized algorithms. For example, primality testing. Machine learning is inherently a randomized algorithm, and that's all the rage today. Routing, conflict resolution, these are all randomized algorithms. What does that mean? It means that those algorithms don't go unless we inject randomness into the algorithm. So probability is playing two roles in computer science today. Probability is the way we analyze the behavior of our algorithms in the real world, because the real world has randomness. And also, we inject randomness into algorithms, and so we need probability to analyze those algorithms. So probability is so fundamental. Okay? And then we talked about, once we've understood that probability is fundamental, and once we've understood the basic infrastructure of probability, you do a complex experiment, it has an outcome, and then you measure something, and then we summarize the entire experiment by the expected value, which tells you, in some sense, on average what happens, and then the variance, which tells you how good that expected value is. How good is that summary of the experiment? Okay, so that's the short stroll through discrete math. Okay? And it's a lot of material, and it now is, might be a good idea to go and reread the material, redo the exercises, redo the pop quizzes, and so on and so forth. It's worth mastering discrete math, especially since it's going to be fundamentally the core of the next part of this course, which is the digital computer. And what has been more impactful than the digital computer? Well, you can go through history and find a few things that have, but certainly the digital computer is one of the most important arrivals into society, at least in modern society. Okay.